Okay, so I apologize. I changed the title. It's very hard to. I was trying to gauge what talk to give, and I was wanting to give a more general talk and something a little less specialized. But then I changed my mind again. So I'm going to have to change the title and abstract on the website again. But the original title was something about inference of mobilities and diffusivities, which I will get to. But I wanted to just have a slightly more general title because I wanted to present our very non-rigorous, blunt instrument for, sort of motivated from physics, from field theory, to look at reconstruction of parameter functions. Okay, so the outline is as such. So I'll first introduce this. This is, it's not really that new. It's really casting things in terms of a field theory is essentially a regularization in inference. And I'll give a couple of examples that using this method, using this formalism, if you will, interpolation of functions, source recovery, dielectric reconstruction, and then finally I'll apply this to dynamic force spectroscopy. This is using an AFM or a optical trap to pull bonds apart and trying to infer the bond potential, the effective bond potential, or the potential of mean force, if you will. And also the diffusivity, and I'll show that you have to do these two together often for things that make sense. And then if there's time, I want to tell you a little bit about what we're struggling with now, trying to reconstruct locations of cellular focal adhesions on substrates. Okay, so let me get started. So path integral based interpolation. So suppose we have, you want to reconstruct some function from measurements of this function, right? Basically interpolating. So usually you take some kind of cost, some penalty, weighted by how much you believe, your measurement error, if you will. And then, so these are the points. Let's say these are my points here. This is the function. These are my measurement points. And the width of the dots are maybe your confidence level that you put into that measurement. And if you just had this, you would get some, this red dashed line would be a solution, would be a minimizer of this, right? But you really, in physical applications, you might want some smooth functions, right? You want something that looks, there'll be some prior that you want, right? So if you think about it, I want some smoothness. You're imposing some kind of prior knowledge onto your function. So we could put in some kind of regularization term, right? Some differential operator squared, right? Some kind of Gaussian penalty for these sharp kinks, if you will. And there's some kind of regularization weight, there's sort of very heuristic ways of trying to self-consistently define this, but you can choose something, and if you choose this very large, then you get something very, very smooth. If you choose it smaller, then you get something very smooth. Okay, so these are standard methods for approximation, okay? But, okay, so I can take this, and for the rest of this talk, it'll be useful to integrate by parts. I'm going to be sloppy with the end conditions and the boundary conditions and whatnot, but so we just integrate by parts, probably some boundary terms. So again, this I'll call the Hamiltonian, the regularizing Hamiltonian, and that will control the smoothness. We can smooth this problem out, and if this is large enough, we can hopefully get some kind of a convex problem. And as I mentioned, this gamma is related to some prior knowledge, which will become clearer later. Okay. So now we want to think about, let's take this. Usually you minimize this, right? But in physics, if you just minimize this is what's called sort of the classical solution, right? But then you really have fluctuations about this. Or you can think of this as, or we can think of it as using this to try to find a way to find the probability distribution over the reconstructed function, right? That's this function that you want. So instead of finding the function that minimizes this, we want to find a distribution of functions, right? So over this function space. So, for example, this function here, the one in blue, light blue, I hope you can see that. This is the one that minimizes h, but this is also a good solution. That's pretty close to minimizing h, right? And this one as well, and this one as well, right? So there's a whole distribution of these functions that would interpolate well. And each of these would be assigned a probability, right? There's a probability that this is the right one, that's the right one, that's the right one. Okay, so the way to do that is just to raise it up in the exponent, right? That's the sort of standard physics way. But I can recast things in terms of Bayes' rule as well. Likelihood, this is prior, right? So this prior, as I mentioned, was the regularization term. So we're going to relate this to e to the minus beta h reg, right? And this is the likelihood. This will be the data term, okay? Or something similar, or something from simulation or whatnot. Normalization. And then this would define this is how I'm going to interpret Bayes' rule now, is as a probability, given some observable, that the function is phi, right? Okay. So this is the posterior, and this is what we want to look at. So the mean field in the physics language, the mean field would be the one that maximizes this, or minimizes the h that's in the exponent. Okay. And then, so the advantage of looking at a probability over function space is that we can do uncertainty quantification, right?
So Tom, when you say mean field, you talk about the minimizer of h, or you include also fluctuations in your mean field?
No fluctuations. Yeah, this is just minimized, right? Fluctuations then would be what I'm going to use semi-classical approximation. So to look at uncertainty quantification. Okay. So uncertainty is really related to the deviance, the deviation from of the posterior from the mean field. Okay. So right. So this is I'm going to write this again. Just rewriting it. So this is the likelihood, the typical one that we use, the prior, and right, we can write this in terms of sort of a functional integral representation, right? A path integral, if you will. Okay, and we again choose this based on prior knowledge of correlations in this sense. Okay. What else do I want to say? That's about it. Okay, so if you look at this, I've turned this into something that looks like field theory in some sense. You've got, so if you look at this is quadratic in phi. This is quadratic with a cross term. Right? This is known, this is given, this is data at points measured x sub m. So it turns out it's really the standard Gaussian form of a functional integral, right? Quadratic and the linear term. And you can do, and this is the normalization. I want to integrate over all possible, since pi, the posterior is a probability over function space, if I integrate over all functions, that should be normalized, and that's just my z0. Okay, and I can do this integral, and that's my result. Okay. So this A, remember this A here couples the two fields. It includes terms from regularization and this quadratic term from the data. Okay, so this A really is made up of two parts, the regularization and the observed part. The B comes from this cross term, right, from the data with the function you're trying to reconstruct. Okay, so the A regularization is this term, and the A data or observed is this. This is from the data, and then the B, as I mentioned, is from the cross term. Right? Okay. So we have that. So it's Gaussian, and well, in that sense, it's solvable. It's exact. I can. So why did I call this ZJ here? Z0. Sorry. Right. 0 is, for those of you that know language, I can add a linear term here, and I set that to 0. That's the source term. Right. Adding a j. I'll show it later. Right. This partition function really is a generating function, right? And I generate it with the generator j here, which I set to 0 in this case, just for normalization. Okay. So if I put in another linear term, I can calculate all integrals, all correlation functions, right? All correlations of the reconstructed function I want to get, that interpolates my measurement points. Okay, so that's just interpolation, all right? That's useful, but suppose now we want to look into some biophysics problems, right? Or applied math problems, engineering problems. So suppose now we want to recover a function, which I'm going to call xi. given measurements of another function that's related to xi. So I measure these at points x of m. So what do I mean by that? So what relates these two is maybe a PDE or something, right? Right, so there's some constraint between these two. Okay, so this could be, xi could be the source. Let's say we're interested in the Poisson equation. That could be the source, and this is the potential that I measure. Right, so that would be source recovery, which I'll mention. Right, so that's a constraint. And in the case I just mentioned, the constraint is Poisson's equation. Right, so there's a constraint between these two. Now I want to convert this formalism to be able to include this constraint. Well, one way is just to put this functional delta function in for f. I just add this constraint in. Okay. So I just put this in, and then this is now you see this is written in terms of xi. Right, so xi is the function we want to reconstruct. It's not the measured function. The measured function is phi. Right? Before they were the same, but now the xi and the phi are related through this constraint, which I will just put in through this delta function. Okay, so now we have, right, this multiplies everything. I want to put everything in the exponent, so it looks like a energy of some sort. So I take my functional delta function and just decompose it in Fourier with a Lagrange function, right, lambda, and there's a functional integral over lambda. Okay, so now I can write this posterior in this form, right? And this h is the total information Hamiltonian, if you will, right? And now it's a function of three variables, the two that are constrained, this Lagrange function, and the observed data. Okay, and now the normalization is this functional integral over all three variables, and then we can write the sorry. So the h is now this, right? When I decompose it like that. Okay. Okay, so the mean field, what I call mean field, will be essentially minimizing that h, right? Which is just nothing other than the Lagrange Euler-Lagrange equation. Okay. So we minimize. Well, the derivative with respect to lambda, the functional derivative with respect to lambda, just gives me that constraint. That's my PDE. That's Poisson's equation or whatever equation you have. And then the other two terms, the other two include the data. Well, this one includes the data. That has a constraint in it. So the data is in here, right, through this delta function. So we solve these equations and we can find the fields, the least action fields, if you will. Okay. So we can integrate over. So we could, you can define an effective energy if I integrate over the lambda and the phi, right? I can find an effective Hamiltonian in xi. Okay. That, however, may not be Gaussian anymore, right? Everything was Gaussian when I was just doing interpolation, but now I have a functional relationship between phi and xi, right? That will not give me a Gaussian, a quadratic energy. This will not be quadratic in xi anymore, in general. So one approach would be to use a semi-classical approximation. Take the extremal solution and then just add the perturbation to it. Okay, and then just turn this into a quadratic again. You see, this is yet another quadratic. Okay, so that's one approach. Right, that's for small. That's local. That's for small local variations around xi star. Okay. And you might ask, well, is this positive definite? And no, we can't prove it in general, actually. But the idea is that hopefully near xi star it will be, okay? Some region around xi star. So I said this was kind of blunt and non-rigorous, but this is sort of my physics approach. So let me run through three quick examples. One is the interpolation problem, membrane deformations, right? And I'm going to use a health-free energy model for that. Source recovery. So this is Poisson's equation. Suppose I measure phi at certain points, and I want to reconstruct rho, right? Another problem is the dielectric recovery. Suppose I know rho, so black is known or measured, and red is what I want to reconstruct. So in this case, this constraint would be, suppose I know the source, and I measure the potential at certain places, I want to reconstruct a dielectric function, right? Okay, so the interpolation problem. So we mentioned that the regularization should be based on some prior knowledge. So in this case, since this is an easy problem, I'm measuring membrane deformations, but I know the model for membrane. Well, one model I'm going to use is the Helfrich-free energy model. In that case, the regularization is easy. It's based on physical principles, right? So that's my regularization. That's the bending rigidity term, surface tension term, right? Fourth order derivative in the Laplacian. Okay, that's a standard membrane mechanics problem.
Sorry, that's because you know you're in equilibrium, and that's going to be something like a Boltzmann weight, so it should be
Yes,
exponential
yes,
in that
that's right,
form.
that's right, that's right.
You know that.
I expect the smoothness to be obeyed by this, right? If I measure certain, so I have a membrane and I can only look at certain spots on it and measure the height, let's say, right? And I know the height, the energy. I mean, I know it can't be kinky like this, right? The membrane.
But it's in a sense you know the probability cost.
That's right.
What
That's
H
right.
is.
That's right. I know that it should be suppressed by these regularization
But
factors.
also you're assuming small,
Yeah,
Right.
definitely.
you don't use it non-linear.
No. That's right.
But the theory you could.
Excuse me?
The theory you could, right?
Yeah, you could if you had a rule for that or some other prior. Yeah.
How is this different or better than if you trusted that model than just trying to get the parameters kappa and sigma?
Okay, so we are not trying to get kappa or sigma yet, and I will discuss that. That's another step. I'm not getting kappa or step. I'm assuming I know kappa or sigma. I'm not trying to reconstruct this, but I suppose that I know this, and I just want to find the functional form of the surface. And then what you really want to do is to reconstruct this, and that would be empirical Bayes, which I'll get to in the next example. But that definitely, that's a good point. So oftentimes you might want to reconstruct this, right? You want to observe the fluctuation of the membrane and say, well, what are the kappa and what are the sigma? I'm not doing that here. I'm just using this as an example for interpolating the function that I measure, right? But indeed, you can do that, and I will shortly mention that. Okay, so I mentioned this J here, right? If I added a source term, so here's my operator. Suppose I know this, okay? This is my Euler-Lagrange, and now I will solve for phi, okay? Or I could consider fluctuation. This would give me the classical solution, but now I want to look at fluctuations. I would take this again, this partition function, add the source term, and then take functional derivatives with J to find the moments, right? The mean, the expected value, and the correlations. Okay. And this is the Green's function for this operator, this P, this thing here. Right? Okay. You take this, reconstruct this, and then you can find all the correlations and all the moments. And this is just one simulated example. So we just simulated using the Helfrich free energy, right? Drew samples of heights, and then sampled some of these. I forget how much. It's from 100 points. Only taking 100 points and then sampled and then interpolating the function. And then the next the uncertainty quantification is I'm going to take the trace of this correlation and plot that, and it's here, right? You see this is the uncertainty actually in this measurement. Okay. So there's a way to take some data, some realization, measure it at 100 points, interpolate the surface, and then even tell you something about the uncertainty, right? Just using this formula. This is just a simple description of
How does this
how you would
compare to
approach.
the actual data? Like what if,
Well, you could tell it looks. I mean, this is the uncertainty, which is smaller compared to that, and that's looks right. So okay. So the question now is, right? You're getting ahead of me, but the regularization parameter in this problem, the beta, the bending rigidity, and the surface tension were regularization parameters, right? And typically, I said there's a prior, and you have to put that, or you can tune that. You can, like for example, in image reconstruction, you tune that parameter just to get something that looks good, right? Here, I'm assuming we knew it. So this is the same beta. This is the same, right? So this is the right correspondence. But if you didn't know beta, and kappa and sigma, the bending rigidity parameters, you would have to tune those until you got something that looked, until you minimize some other metric between the two. And that other metric could be based on the data itself, like the marginal likelihood, right? So you can self-consistently find the regularization parameters.
Tom, you seem to have more uncertainty in the corners. Is that because you have an open system that you're...
Uncertainty in the corners.
Yeah, they seem to have little peaks.
I
I would have thought you'd have a
probably.
periodic system.
This was not. Yeah, I don't remember. Yeah, it's.
Sorry.
Yeah. Like I said, we just sort of ignored the boundary conditions. I just wanted to keep it simple. It is due to certainly the form of the Green's function. And that's why you get these sharp little spikes for all Green's functions where these operators look something like that. So yeah, there's something at the corners that's happening. Anyway. Okay. So for source recovery, now the problem, again, is this harder problem because I have to put in this Lagrange function. And now there's three Euler Lagrange equations. One is the Poisson equation back again. One is the one with data, and this is it. Okay. So it's the same prescription here. This is the function I want to reconstruct, right? Which I'm going to write in terms. I've already applied this constraint here in this equation, right? I just took this row. This should have been a row and a row, and I'm just putting the Laplacian here. So I can have it in terms of one function. And again, I put in a source, and I take the moments and the mean, so I can find the expected value, and as well as the correlation. And this is, again, a test example. So this is the ground truth. I have a source which I know. This is the solution, right? And then I sample these points, I think 100 points or something like that here. Put in some regularization here, and
what is some regularization?
say that again.
Which regularization?
What sumness?
So which P? I forgot. What P did we use?
Was that before?
I think it was just grad. I think this. Yeah. Sorry, I didn't. Yeah. There was a regularization term. I think it was probably just grad rho squared. Yeah. I believe we just used grad rho squared with some coefficient in front, which I didn't put in here, but we tuned it, by hand. I mean, we don't have any prior knowledge on what the source should be, right? We don't have any. So we just did it. This is just sort of eye by eye what looked good. We didn't really. There's really no physical rule that there's no process in getting this row, right? So if you can imagine if you had some material where you had phase separation in source or aggregation of something, you can put in, use something phase field or something like that for the regularization, right? So this is just to show, that this is how the procedure works. So you sample, and you can do interpolation, and you can reconstruct the row. You can do interpolation by itself, or you can do this process and reconstruct both of these, the average function, and then here's the uncertainty as well. Okay, and then the dielectric reconstruction is even more complicated. So now we have a regularization for the dielectric function. And this function, for example, dielectric, if you're making a material, and the dielectric, and it's a phase-separating material, and the two different phases are different dielectrics, you can maybe put in here, this would be based on how you expect the material to have been made, for example, right? A phase field problem. And then here are the Euler-Lagrange equations. And again, if you integrated these out, you'd get a non-quadratic effective Hamiltonian for this, and you'd have to do perturbation. And this was a lot messier, so I won't show anything. But so let me move on to dynamic force spectroscopy. So we're going to apply this to the problem of pulling a bond apart, right? Either using AFM, optical trap. So here's the bond attached to a substrate. This is what I control. I pull this up at some speed. There's a deflection because the cantilever has a spring constant. And then the deformation of the bond, this is going to be my measured. I'm actually going to measure, I know this, and I measure this. I shine a light off this. I can measure D. I control this. So based on that, I'm really measuring xi, right? I'm measuring the displacement, okay? And I'm pulling this. And here's a trajectory might look like this, right? As I pull this with some fixed velocity, right? I pull this up. Here's a D, and what happens is the bond could break. This bond could break, and then you get the D would jump right back, okay? So usually you pull it until it breaks, and what are the information here? The trajectories, as a function of time, and the time at which it breaks. Right? The time at which it breaks, you know this L, and you know the deflection. If you know the bending stiffness, then you know the force at which it broke. Right? So those are things people measure. And from that, what do you want to say? You want to say, what is the bond potential of this macromolecule that I've got? Right? So we pull. The pulling position is defined. It's given by a force that pulls this up. And the bond displacement is just this L minus this D. Okay, so typically what's done, either a parametric form. I'm going to assume that the bond takes some parametric form, pull it, measure bond rupturing rates, for example, right? The force at rupturing as a function of loading rate. For this, for example, you pull, and then it ruptures and it breaks. And you can measure the position of this rupturing event. Right, so this is all it's very parametric, right? This is escape over a barrier. You pull, the barrier gets lower, and it breaks off, right? So depending on how fast you pull and the position of this braking force, you try to reconstruct what the potential looked like. Okay, so there's a lot of work that have been done using parametric bond bending. Another approach is maybe use work theorem, right? I can measure how much work it took for me to pull from one position to another. Okay, then from that, I will know the difference in free energy, right? If I take the work, I take the average of this work, that's just exponential of this energy. And that's based on work theorem ideas, okay? And the first case has limitations in terms of a parametric form for the bond. This process, while it requires an initial distribution, an initial equilibrium or steady state distribution, right? It's often difficult to get enough sampling for this, to be able to sample this properly. There's no likelihood, so there's nothing you can use that's for uncertainty quantification, okay? And then finally, there's no handle on the diffusivity. This only reconstructs the bond potential, right? Nothing, it doesn't say anything about the diffusivity, how the diffusivity might also depend on the coordinate.
What do you mean by diffusivity?
I mean the mobility of the bond coordinate as I'm pulling. right? That's always assumed constant, even in these parametric models. I mean, they don't have to, right? I can assume that right, so here's a potential, and as I'm pulling it out, the diffusivity could be different along this coordinate, right? The resistance, the friction, if you will, right, along. So there's nothing that says that, you know, you can imagine a bond if it has sort of you're pulling along one direction, one main direction, but it's got sort of, it's a high 3n dimensional, right? It's got orthogonal directions. If I spend some time in an orthogonal direction, it'll look like I have higher diffusivity there, right? So physically, that would be the origin of this variable diffusivity. And so none of these really methods do that. So what we're going to do is we're going to try to do that. Okay, so we write down this SDE. Here's the drift, right? Now I'm going to assume that this fluctuation dissipation, so this drift will be proportional to the diffusivity. Right? That's the mobility, and it's got the derivative of the mobility of the diffusivity. Sorry, right? Because now it's spatially dependent. And this is my associated Fokker-Planck equation, where the total potential now, right, this potential in here, this total potential is the bond energy part plus this harmonic part that I'm pulling, plus the pulling part with the spring constant, okay? So that's the total potential that I'm under. This is the molecular force. This is what we're going to reconstruct, and the bond mobility. We're going to look at these two as separate things to reconstruct, okay? And we're going to assume that it's pulled with this constant velocity, as I mentioned, and the applied force, this is equivalent to measuring this, right? Because it's L minus D. Okay, so when we measure this, we're measuring the applied force, okay, or the deflection of the cantilever. So we're going to avoid the parametric form for these, and the goal would be to reconstruct the force, the gradient of potential, this part, the U, and the diffusivity from these measurements at time Ti. Yeah.
This requires many trajectories?
That'll be in the uncertainty quantification. It requires some, yes.
I mean, this is not really a reproducible experiment. You get exactly the same bond every time.
Yeah, I'll say something about that. Yeah, there's some uncertainties. I'm going to do the simple case where we're sure that it's the same measurement, right? So I'm assuming identical pulls. You pull it, break it, you reattach, pull, break. Yeah. How many times you can do it? Maybe tens, hundreds, I suppose.
You don't have to assume it's exactly identical, it's statistically identical, right?
Excuse me?
You don't have to assume it's exactly identical, it's statistically
No, statistically, that's what I meant. Yeah, sorry. Yeah. Okay, so we want to put in a regularization for the force, right? Because I'm measuring at discrete points. So the functions I want to reconstruct are f and this d, or I'm going to call it g. Right? I'm going to take some kind of a log normal assumption about this diffusivity. Right? Diffusivity is positive. So I'm going to take this g that runs from minus infinity to plus infinity if I take the log. Okay, so my regularization terms now will be in f and in g. So I have two. Okay, this is the bond. This is the diffusivity. Okay. So we're just going to, the prior distribution is just enforce Gaussian spatial correlations. That's it, right? And we have to tune those parameters. And the trajectories are measured at these times. And so now the likelihood function is known, right? It's not this quadratic term that I had before. It's known because I have the solution to the Fokker-Planck equation, right? For small little time increments. So this is the delta t is the time increment taken between measurements, and this is my likelihood, right? This is a given. So the xi's are measured. Alpha are the different trajectories, right? J is the time, and alpha is the different trajectories. I'm assuming that they're all independent here. Okay. So here's the d, right? This is the data term. These are measured data terms, but these are the functions that we can reconstruct. The d and the a. Remember, the a is the drift, and the drift has the force in it, right? Has the potential in it. Okay. So both d and u, the potential, are in here, as well as the data. So this is the data term that couples to the functions I want to reconstruct. Plus, I have to add the regularization terms, right? And then this is my This is the same as before. So that's the likelihood, that's my regularization, right? And the total Hamiltonian is just this term here. Right? So I've only pulled out the parts that depended on D and F, or U. D or G, F or U, right? F and G here, those are the regularization terms. So you can do Euler-Lagrange, and let me just, so Euler-Lagrange is this, and you see this is an operator, this is a delta function, so I can actually solve this, right? So away from the data points, it's just the Green's function of this, and then you add the sources at the delta function. They depend on, of course, F and G. So this becomes a large system of equations at these discrete points where you measure, or your measurements, and you can solve those numerically and get F star and G star. Okay. Okay. So the regularization that we use is just a very generic term. Assume it's infinitely differentiable, and we just take this, take these forms. And there's two parameters. One sets the spatial scale, right? Oh, okay. One sets the spatial scale, and one sets the magnitude. Okay. So at the end of the day, right? This is related to your question about reconstructing the bending rigidity of the surface tension, right? So these, what do we have to find these self-consistently, and a simple way is just use the empirical Bayes, which is to maximize the marginal, right? Just maximize this probability as a function of this theta, of the parameters, okay? So there's 4 parameters here, and we can do that to find the betas and the gammas that are in this regularization, and we can then look at uncertainty quantification by taking the semi-classical limit, and there's a lot of horrendous algebra here and numerics, but at the end of the day, let me just get to it. Right, so this is the marginal likelihood for theta. I have to minimize this to find my coefficients, right, that determine F and G, find F and G, and then do this, find F star and G star, do the semi-classical approximation, and so here's sort of the sequence of this is the outline of your procedure. So you have to estimate this too, and I didn't get into that. So when I talk about diffusivity of the bond, the whole apparatus has diffusivity, right? The whole cantilever and all the attachment stuff. So you have to subtract that out. There's a way of doing that self-consistently. So we have to subtract out the background diffusivity, find a choice of parameters, choose these parameters that minimize this, and then update my F star and G star. And here's some simulated data. These are some trajectories. The green is the weight of the trajectories. These are for 2 different potentials, which I will show here. This is one of the potentials. I think this one corresponds to this one here. So the red dashed line is the ground truth. It's some complicated potential with two minima, and this is the reconstruction where I fix the diffusivity to be just my background diffusivity. And then the blue line, the black line is the unregularized, right? There's no regularization, so it's not smooth. I add the regularization, I smooth it, and here's my reconstruction, and it's not that good, right? And then here's another potential. This is the one on top. This is a much more complicated potential, and I don't really get it right, okay? That's by fixing the diffusivity. Now if I do both the diffusivity and the potential together, for those 2 potentials, here they are. So the red line, again, is the ground truth, and this is the diffusivity function that we put in, right? This is D0, but let's say we put a dip in here. Let's say it sort of gets sticky somewhere down here, and the reconstruction, and the gray line is the unregularized, right? So it's very messy. And then this is for a certain number of trajectories. That's that coefficient alpha, the sum over alpha that I took, right? The number of trajectories. So this is, and then the yellow is the 95% confidence bands from the correlation function, right? Okay. So you see it works okay, right? So this is F and D. F is the gradient, minus gradient of the potential. So this really isn't the potential, it's the gradient of the potential, but you know. And then this is the diffusivity. Okay, so that's our approach on this problem, and I think 2 more minutes. Okay, so I just wanted to briefly mention some other things that we're trying to do with this. And so one problem is the reconstruction of focal adhesions. If you have a cell or a group of cells that are migrating on a surface, they're attached and they walk, right? And they stick to the surface and they move, and you want to reconstruct. Actually, probably hearing all the earlier talks today, there's probably some super resolution method that would render all this obsolete. But anyway, suppose if you wanted to reconstruct where the attachments were and how strong they were, right? How would you measure that if you couldn't image it? Well, one way is to put in fiduciary markers, right? Little gold particles or some dust or something into the substrate, into this gel. Here's a cell, outline of a cell. Here are the focal adhesions, pulling it, walking, right? And so it'll distort the gel underneath, and then you can measure the distortions of these little fiduciary markers. Right? That's a displacement field, if you will, of the substrate. And from measuring that, can you reconstruct where so this is like source recovery, right? But source recovery in the elastic problem. And you can write the Green's function for the substrate here, just using elastic theory, Young's modulus, Poisson ratio. That's your Green's function. And what you're trying to reconstruct is the in-plane stress distribution of these cells. And so the first thing to do is to define my cost, right? So the cost, it would be this, the data, the displacement, U, data, and U model. U model is simply the Green's functions times the surface stress. Okay, so that's the U model. And the U model has the surface stress in it. So we're trying to reconstruct the surface stress function, the whole function, based on this, but we need a regularization term for the surface stress, right? As we mentioned. So what kind of terms can you use? Okay, so you want the surface stress to be rotationally invariant. You want anything that you reconstruct to not depend on your frame of reference, right? So I can take this tensor of the surface stress, which is a vector, and form the rotationally invariant constructs of it, which is the trace and the determinant of this matrix. So one proposal would be to use this as regularization, okay? And for the surface stress, and then raised to some power, and this power, I'm going to try possibly 1. Oh, okay, it's a couple other things. There's other constraints we need to add to this, right? Just like the constraints for the PDEs we had before. We know that this is, we're going to take the overdamp limit, so it's going to be force-free, so there'll be no force and there'll be no torque, right? It should be force-free, torque-free. So we have to put these in as constraints, right? And so this is my full thing. There's one other constraint. What is that? So one can image is the outline of the cell, typically. So you know the stress should be 0 outside the cell, right? So that's another constraint that you have. Okay, so that's where we're at. We tried we're trying P equals 1. Why? Because the focal adhesions are compactly supported, right? So you want L1. But for L2, here's our test case, and we're getting some results that getting there, it looks like. But anyway, any suggestions you might have would be we can talk about it. Thank you. Yeah.
It's very high level. I don't follow the details. Why you decompose the function into 2 parts? The one that you measure and the other one that might generate it. Cannot this technique apply to the composition directly?
What? Because I don't have access to. You mean the constraint originally, the F?
Yeah, you mentioned 2 functions. One that generates another on which you know to do the regularization.
Right. So
why can't you do it under composition? So dimensionality. What is the?
Well, I don't have access. I mean, I can't. So it depends on what you can measure. Or are you asking a deeper question? So here, suppose I measure the potential with some electrodes in a sample, but I'm not able to measure the dielectric, for example. Right? But I know physically they have to be related to Poisson's equation. Yeah.
really interesting discussions with a great like